Let's be quite honest, traveling to Mars isn't going to be easy. There's a reason why humans have never explored the Red Planet, while only a few lucky and expensive landers have. The trip to and from Mars is long, dangerous, and more challenging than any space mission humans have ever undertaken so far. There are plenty of challenges lurking in the deep reaches of space that make a journey to Mars oh so difficult. For one, humans just aren't used to being in space for so long. A round-trip mission to Mars would last an astonishing 21 months. 9 months to get there, 3 months on the planet, and another 9 to get back. Every single second spent traveling to Mars can be easily translated into energy, fuel, and money. It will cost thousands of dollars a second just to get to the Red Planet. When you think of it that way, and when you think of the damage that all that time in space can do to a human body, you understand the fear and hesitation some have when thinking of traveling to other planets. But what if there were a faster way to get there? What if a trip to Mars didn't have to take a whopping 21 months? What if all that time and money could be saved by a much shorter and safer voyage? There are a growing number of scientists who think getting to Mars much faster is quite possible. Instead of 21 months, why not get to Mars in only 3 days? If these methods of space travel turn out to be effective, it's going to completely change the way we think about living on Mars. Ever since the height of the space race, chemical rockets have been the most commonly used propulsion method. In many ways, SpaceX and their rockets, especially the Starship, look a lot like the old Saturn rockets that Americans took pride in during the early days of NASA. But SpaceX tech is far beyond anything NASA ever created, which will not only save time, but also make the long voyage much more comfortable. SpaceX is currently hard at work on their next-generation Raptor engines, which will power the Starship spacecraft and the Super Heavy rocket. They're known for the ridiculous amount of power they produce, but the truly game-changing aspect is their reusability. Like many engines before it, the Raptor burns chemical fuel to produce thrust. However, its use of liquid oxygen and methane is different from nearly every other engine in the space travel field. No other rocket engine is capable of producing as much energy out of liquid methane and liquid oxygen. The Raptor engine, and the Raptor 2 that's now being developed, is a key piece of SpaceX's future. It has a radical amount of power, cultivated in ways that haven't been used before. With the science and reusability factor, the Raptor engine is what space engineers have always dreamed of, but have never been capable of achieving before now. It will save money, it will save energy, and it will help massive vessels like the Starship transcend our atmosphere and head straight for Mars. But there is still one problem with this sort of propulsion method. A trip to Mars will take roughly 9 months in each direction. So even though the technology SpaceX and other private companies are creating is far superior to that of the past, scientists and engineers are looking for ways to travel between the planets at a much greater speed. This is where a nuclear-powered rocket has a chance to truly transform space travel as we know it. A nuclear-powered reactor on a rocket would generate heat from uranium fuel. That thermal energy would heat up a liquid propellant, typically liquid hydrogen, which will expand into gas and shoot out the back of the rocket. You can just imagine the sort of thrust a nuclear-powered rocket would produce. Scientists predict that a rocket like this would produce twice the thrust per unit of propellant than the current chemical system. That means that an average Martian one-way trip would only take roughly 90 days. But some people are afraid of this approach to space travel. Thanks to the Chernobyl disaster and other past nuclear events in history, it's no surprise that nuclear energy has a bad reputation. However, it's actually a very safe method, and there are particular safeguards in place to prevent any sort of radiation leakages or exposure. And for an even extra layer of safety, any nuclear-powered ship would actually rely on an old-fashioned chemical rocket to get out of our atmosphere. It would only be once the ship left the Earth that it would start using its nuclear power. But what if you need to get to Mars even faster than that? If that's the case, using ion engines may be the next best option. Many scientists are investing heavily into researching these ion engines to see just how powerful these futuristic creations can be. Unlike chemical rockets, ion engines would accelerate electrically charged atoms, known as ions, through an electric field. This would propel a rocket ship forward in an incredible manner. However, an ion engine really finds its potential once it reaches space. Once out of the Earth's atmosphere, the charged ions will be giving the rocket a continuous push. It's been compared to the wind pushing a sailboat. This manner of propellant would get the rocket ship moving far faster than a typical chemical rocket. Spacecraft powered by these ion thrusters can reach speeds of up to 200,000 miles per hour. That's 90,000 meters per second. In comparison, the world-famous American space shuttles could only reach speeds of around 18,000 miles per hour. The trade-off for these high top speeds of ion thrusters is slow acceleration, which is why this method might be perfect for trips across our solar system. Based on the science behind the revolutionary ion engine, you can plan on it taking only 39 days to get to the red planet. Now, let's take a look at the most futuristic and exciting method of space travel that could get us to Mars as fast as possible. A photonic propulsion system would be able to power a rocket in remarkable, jaw-dropping ways. This one-of-a-kind rocket would rely on the momentum of particles of light, known as photons, to move the ship forward. It sounds far-fetched, and it is. There's still so much work to be done in this field. But the idea has been in development by numerous scientists for years now. If they're able to crack the code of photonic propulsion, we could find ourselves arriving on Martian soil in not months, but days. Particles of light don't have any mass. However, photons do have both energy and momentum, and when they reflect off an object, that momentum is transferred into forward motion. By harnessing the power of photons, an entire rocket ship could blast through the galaxy at breakneck speeds. Right now, it's predicted that photonic propulsion could get a small robotic craft to Mars in just 3 days. There's no doubt that photonic propulsion could be a literal game changer. Not only could it make exploration so much faster, but it could also allow humans to travel to Mars and far beyond as well. All of these new, promising methods of travel could radically change how we traverse the galaxy. If we are truly able to limit the amount of time it takes for us to get to Mars and other planets, then a new golden age of space travel awaits. What are your thoughts on these futuristic methods of space travel? Let me know in the comments below. And don't forget to like and subscribe for more exciting content.
Earth is covered in coastlines we've seen 1,000 times. Waves meeting land, tides rising and falling to the pull of the moon. Beaches shaped slowly, patiently, over spans of time longer than human history. We think of these scenes as ordinary, even timeless. But imagine realizing that this same process may have happened somewhere else. Around 3.6 billion years ago, another planet in our solar system may have had its own shoreline. Not blue and green like Earth's, but rust-coloured. Not under a bright sun, but beneath a dimmer sky. 2 small moons rising overhead, tides subtly pulling at dark water stretching toward a distant horizon. This wasn't Earth, it was Mars. For decades, scientists have argued over whether such oceans ever existed. The idea isn't new, but the evidence was always distant, gathered from orbit, inferred from patterns seen far above the surface. From that height, landscapes can be deceptive. Interpretations multiplied. Agreement never quite formed. Then, quietly, that changed. Earlier this year, researchers published results from a rover that had been moving slowly across Mars for years, far from headlines. Not a spacecraft looking down from above, but one listening from below. China's Zhurong rover detected structures buried beneath the Martian surface that resemble something deeply familiar. Coastlines shaped by waves and time. What it found doesn't just reopen the debate about Martian oceans, it reframes it. This is a story written in layers of sediment and silence. A story about how shorelines form, what they leave behind, and how we read the history of a world that lost its water billions of years ago. And it's a story that may help us understand not only what Mars once was, but where we should look if life ever had a chance to begin. Water covers 70% of Earth's surface. It fills our oceans, carves through landscapes in rivers, freezes into polar ice caps, and evaporates into clouds that bring rain. It makes up roughly 60% of the human body, flowing through blood, filling cells, enabling the biochemical reactions that keep us alive. We talk about water as though it's ordinary, and in a way, it is. On Earth, it's everywhere. But when you step back and look at our solar system, water in its liquid form becomes remarkably rare. Mars has water. We've known this for some time. Evidence suggests that water existed on Mars as far back as 4.45 billion years ago, preserved in the chemistry of crystals found inside a Martian meteorite that fell to Earth. Those crystals could only have formed in the presence of hot, water-rich fluids. Martian dust also contains a mineral called ferrihydrite, which only forms when water is present. So Mars had water early in its history, and that water interacted with rock and dust in ways that left traces we can still detect today. We've also found evidence of ancient river valleys carved into the Martian surface, visible in images taken by orbiters circling the planet. These valleys wind across the landscape in patterns that suggest water once flowed there, possibly for millions of years. Mars also has polar ice caps, covering an area comparable to the continental United States. Some scientists think resilient forms of microbial life, if they ever existed, could still be preserved deep within that ice, locked in a kind of stasis that might keep them intact for billions of years. But rivers and ice caps, while important, aren't quite the same as a coastline. Rivers are dynamic, constantly moving, flushing materials downstream. They dilute organic molecules, making it harder for the delicate chemistry needed for life to get started. Ice caps are cold and stable, good for preservation, but not particularly active environments. A shoreline, though, offers something different. Shorelines concentrate organic molecules through evaporation. They provide mineral-rich surfaces where complex chemistry can happen. They offer energy sources, ultraviolet radiation from the sun, heat from volcanic activity, chemical gradients where different materials meet. All of these things can drive the kinds of reactions that might lead to life. If researchers could confirm that Mars once had a standing body of water, a lake or an ocean with a shoreline that persisted for a significant period of time, it would change the way we think about where to look for evidence of past life, and that's exactly what the Zhurong rover's data suggests might have existed. On July 23, 2020, a spacecraft called Tianwen-1 began its journey to Mars. The name translates to Questions to Heaven, a reference to an ancient Chinese poem that asks about the origins of the cosmos. Aboard the spacecraft were 3 components: an orbiter designed to circle Mars and relay data, a lander that would descend to the surface, and a rover named Zhurong, after a god of fire in Chinese mythology. The mission had 3 main objectives. First, to study the surface and subsurface geology of a region called Utopia Planitia, a vast basin that scientists suspected might once have been an ancient ocean based on satellite mapping. Second, to monitor Mars's climate and weather, tracking things like magnetic field variations, dust storms, and how dust affects solar panels and atmospheric conditions. Third, to search for signs of water and assess whether the region could have supported life in the past. Tianwen-1 took 202 days to reach Mars. On February 10, 2021, it entered orbit around the planet. Controllers spent 3 months testing the spacecraft's systems, adjusting its orbit from an equatorial path to a polar one, preparing for the landing phase. Then, on May 14, 2021, the lander touched down on the Martian surface. A week later, Zhurong rolled down a ramp and onto the red soil, making China the second nation in history to successfully deploy a rover on Mars, following the United States. For China, this mission represented more than scientific discovery. It demonstrated their growing capabilities in deep space exploration, their ability to design, launch, and operate complex missions without relying on foreign navigation or communication systems. It also laid groundwork for future ambitions, including a Mars sample return mission and possibly a crewed mission to Mars by the 2030s. The rover itself weighed 240 kilograms and carried 13 different scientific instruments. These instruments could be grouped into 4 categories. First, radars capable of detecting subsurface structures up to 100 meters underground, including a ground-penetrating radar system designed to map layers of rock and sediment beneath the surface. Second, spectrometers that could analyze the composition of soil and rocks, using lasers and infrared sensors to identify minerals and chemical signatures. Third, optical cameras for imaging the planet, both from the orbiter and from the rover itself, providing topographic data and helping with navigation. Fourth, monitors for atmospheric and space environment conditions, including instruments to measure magnetic fields, space radiation, temperature, wind, pressure, and even sound. One of the mission's most memorable features was a small deployable wireless camera that the rover could set down on the surface and then drive away from, allowing it to take selfies. These images became some of the mission's most iconic, showing the rover standing alone on the Martian landscape, a small machine on a vast empty plain, framed by distant hills and a pale pink sky. The rover landed in Utopia Planitia, the largest known impact basin in the solar system. This region had drawn attention from scientists for decades. It was the same area where NASA's Viking missions had landed almost 50 years earlier. But interest in Utopia Planitia was renewed in 2016, when NASA announced the discovery of a massive deposit of underground ice there, containing roughly as much water as Lake Superior on Earth. That's about 12,100 cubic kilometers, or 10 quadrillion liters. Given this promising location and the rover's sophisticated instruments, the stage was set for discoveries that might challenge existing theories about Mars's past. To understand what Zhurong found, it helps to first understand how shorelines work on Earth. This requires a brief lesson in geology, specifically in how sediment moves and where it ends up. Sediment particles, grains of sand, silt, clay, pebbles, are transported across the landscape by wind, water, and ice. Rivers carry sediment downstream. Glaciers push it along as they advance and retreat. Wind picks up fine particles and deposits them elsewhere. Eventually, this sediment settles in what geologists call low-energy environments, places where the forces moving the sediment decrease enough for particles to drop out of suspension and accumulate. Examples of low-energy environments include river deltas, where rivers slow down as they meet the sea, lake and ocean floors, where water is relatively still, floodplains, where rivers overflow their banks and spread out, losing speed, the bases of hills and mountains where material that has been eroded from higher elevations comes to rest, and coastlines, particularly a zone known as the foreshore. The foreshore is the part of a beach between the high tide line and the low tide line. It's dynamic, meaning it changes constantly depending on factors like wind strength, tidal cycles, weather events, and the type and size of sediment particles present. Sediment can be added to the foreshore when waves push material up the beach, or removed when waves pull it back out to sea. Over time, though, a balance tends to form, and this balance gets recorded in the geological layers that build up. On Earth, foreshore zones typically slope gently toward the water. The angle of this slope depends on what kind of sediment makes up the beach. Beaches composed of fine sand tend to have low gradients, sometimes just a few degrees. Beaches made of larger particles like cobbles or pebbles can be much steeper, sometimes reaching angles of 15 or 20 degrees. These sloping layers represent the long-term interaction between sediment supply, wave energy, and water level. And under the right conditions, these layers can be preserved in the geological record for millions of years, buried beneath younger sediment, waiting to be discovered. This is what makes shoreline evidence so valuable. It's not just about proving that water existed, it's about understanding how that water behaved, whether it was stable or intermittent, whether it supported processes that could have been relevant to the origin of life. A river valley tells you water flowed. A shoreline tells you water stood still long enough to build something lasting. Zhurong spent its time on Mars doing what rovers do best, moving slowly across the surface, stopping frequently to examine rocks and soil, sending radio waves into the ground to map what lies beneath. The ground-penetrating radar worked by transmitting radio signals downward. When those signals encountered a boundary between two different types of material, say, a layer of fine-grained sediment sitting on top of coarser sand, some of the signal would bounce back to the rover. This created what scientists call a reflector, a bright line in the radar image indicating a change in subsurface composition. As Zhurong moved through Utopia Planitia, it detected these reflectors, 76 of them to be precise. And what caught the attention of the research team wasn't just that the signals were bouncing back, but the angles at which they were bouncing back. All 76 reflectors sloped in the same direction, at angles ranging between 6 and 20 degrees. This was unusual. If the structures had been formed by wind-driven sand dunes, you would expect slopes pointing in multiple directions, because wind direction changes over time. If they had been formed by ancient lava flows, you would similarly expect variability, as lava doesn't flow uniformly across a landscape. But these reflectors all pointed the same way, consistently, across a stretch of terrain measuring 1.3 kilometers. The team analysed the data and concluded that what they were looking at lay 10 to 35 meters below the current Martian surface. They compared the radar profiles to similar structures found on Earth and discovered something striking. The buried beach deposits in the Bay of Bengal showed remarkably similar patterns, sloping layers at comparable angles, formed by the interaction of waves, tides, and sediment supply over extended periods of time. One of the co-authors of the research paper explained it this way: "It's a simple structure, but it tells you there had to be waves. There had to be a nearby river supplying sediment. And all of these things had to be active for some extended period of time. Not just a brief event, but something sustained, something that left a record in the geology." The team also considered the possibility that tides might have played a role. Mars has 2 moons, Phobos and Deimos, and while they're much smaller than Earth's moon, they still exert gravitational influence on the planet's surface. The Sun also contributes to tidal forces. If an ocean existed on ancient Mars, these forces could have created tides, adding to the wave action that shaped the foreshore deposits Zhurong detected. The simplest explanation, given all the evidence, was that these sloping layers represented an ancient coastline, a place where water met land and interacted with sediment in ways that left structures we can still detect today, billions of years later. For decades, the question of whether Mars once had oceans has divided the scientific community. Some researchers have argued passionately in favour of the idea, pointing to geomorphological features visible in satellite images, valley networks that suggest river systems feeding into low-lying basins, smooth plains that could be ancient seafloors. Others have been more skeptical, suggesting that what looks like shoreline evidence could be artifacts of image resolution, or features created by processes unrelated to standing water. And part of the difficulty comes from the fact that most of our observations of Mars have been made from orbit. Satellites can provide broad coverage and identify large-scale patterns, but they lack the close-up detail that ground-based measurements offer. Without being able to walk up to a rock formation and examine it directly, without being able to drill into the soil and analyse its composition layer by layer, interpretations remain somewhat open-ended. Zhurong's findings represent something different. This is the first on-the-ground data ever collected from a suspected ocean zone on Mars. The rover didn't just take pictures from above, it sent radio waves into the soil and mapped subsurface structures directly. This kind of data is harder to dismiss as an observational artifact. But even with this new evidence, questions remain. The most pressing one has to do with climate. If Mars had oceans 3.5 billion years ago, how was the water able to remain liquid? This brings us to a problem that has puzzled scientists for years, known as the faint young sun paradox. 3.5 billion years ago, our sun was about 25% dimmer than it is today. This might not sound like much, but it makes a significant difference when you're trying to keep a planet warm enough for liquid water. Earth, which is closer to the sun than Mars, managed to stay warm during this period, likely because of a thick atmosphere rich in greenhouse gases. Mars, being farther out and receiving less sunlight, should have been frozen solid, and yet the evidence suggests that Mars was not frozen. River valleys, lake beds, and now potentially ocean shorelines all point to the presence of liquid water on the surface. This creates a paradox. If the sun wasn't providing enough heat, where did the warmth come from? Scientists have proposed three main theories to explain this. The first theory suggests that Mars was warm and wet for an extended period. In this scenario, Mars had a thick atmosphere loaded with greenhouse gases, primarily carbon dioxide and water vapour. This dense atmosphere trapped heat, creating a greenhouse effect strong enough to keep surface temperatures above freezing for millions of years. This would explain the evidence for rainfall, rivers, lakes, and oceans. The problem with this theory is that carbon dioxide and water vapour, according to current climate models, don't produce enough warming on their own. You would need additional greenhouse gases, methane, ammonia, or molecular hydrogen to create the temperatures necessary for widespread liquid water. But these gases are chemically unstable in the Martian environment. Ultraviolet radiation from the sun breaks them down quickly. Maintaining high concentrations over millions of years seems difficult without a continuous source to replenish them. The second theory proposes that Mars was only warm and wet intermittently. Instead of a permanently warm climate, Mars experienced episodic warming events triggered by major geological activity. Massive volcanic eruptions could have released huge amounts of greenhouse gases into the atmosphere. Large asteroid impacts could have generated enormous amounts of heat, melting ice, and creating temporary warm, wet conditions. During these warm spells, ice would melt, rivers would flow, erosion would occur, and sediment would be deposited. Then, as the gases dissipated or the heat faded, the planet would return to a frozen state. This theory has appeal because it doesn't require Mars to maintain a thick atmosphere indefinitely. It allows for the observed evidence of water activity, while acknowledging that the planet probably spent most of its history frozen. The challenge is determining whether these episodic events would have been frequent enough and long-lasting enough to produce all the features we see. Would a series of brief, warm periods be sufficient to carve the extensive valley networks that crisscross the Martian surface? It's possible, but not certain. The third theory suggests that Mars was cold throughout most of its history, with a landscape dominated by ice and snow. In this scenario, water existed primarily in frozen form. However, under certain conditions, orbital changes that altered how much sunlight different parts of the planet received, or localized heating from volcanic activity, ice could melt temporarily. This would explain why Mars shows signs of both glacial processes, ice sheets advancing and retreating, and flowing water, rivers and floods. The difficulty with this theory is explaining how enough ice melted often enough to produce the erosion features we observe. If Mars was mostly frozen, what caused repeated melting episodes? Orbital changes occur over long timescales and might not provide consistent enough heating. Volcanic activity is localized and might not affect large regions simultaneously. None of these three scenarios perfectly accounts for all the evidence. Each has strengths and weaknesses, and this is where the discovery of a potential ancient shoreline becomes particularly interesting. Shorelines imply not just the presence of water, but the persistence of water. They suggest stability over time, enough for waves to shape sediment, for tides to cycle, for geological layers to build up. If the Jurong data is correctly interpreted, it strengthens the case that Mars had at least regional bodies of standing water that lasted for geologically significant periods. But it also makes the climate puzzle more pressing. How did that water stay liquid? Solving the faint young sun paradox may be the key to understanding whether Mars was ever truly habitable, and if so, for how long? When scientists talk about habitability, they're not necessarily talking about whether humans could live somewhere. They're talking about whether the environment could support life as we understand it, even in its simplest forms. And for life to get started, certain conditions seem to be helpful. You need liquid water. Life as we know it requires water as a solvent, a medium in which chemical reactions can occur. You need a source of energy. This could be sunlight, chemical energy from reactions between minerals and water, or heat from volcanic activity. You need organic molecules, the carbon-based building blocks that make up proteins, nucleic acids, and other essential components of living cells. And you need time, enough for random chemical reactions to stumble into configurations that can self-replicate and evolve. Shoreline environments offer several of these things. When water evaporates from a shoreline, it leaves behind concentrated solutions of dissolved minerals and organic molecules. This concentration can promote the formation of more complex molecules. Shorelines also provide surfaces, rocks, sand, mineral grains, where molecules can absorb and interact in ways that might not happen in open water. They offer energy gradients, differences in temperature between sun-warmed shallows and cooler depths, chemical differences between fresh water flowing in from rivers and saltier ocean water. Contrast this with rivers, which are constantly moving. Rivers dilute molecules, flush materials downstream, and don't allow much time for delicate chemistry to unfold. Ice caps, on the other hand, are cold and stable, good for preserving things that already exist, but not particularly conducive to the active chemistry needed for life to begin. If Mars had stable shorelines, places where water lapped against land for thousands or millions of years, those would be among the most promising locations to search for biosignatures, chemical or physical traces left behind by living organisms. Microbial mats, layered communities of bacteria, might have formed in shallow water. Stromatolites, rock-like structures built by microbes, could have developed in tidal zones. Organic molecules produced by metabolic processes might have been preserved in sediment layers. The challenge, of course, is that 3.5 billion years is a very long time. Mars has been cold, dry, and subjected to intense radiation for most of that time. Any organic material left on the surface would likely have been broken down. But beneath the surface, protected from radiation and chemical weathering, traces might still exist. This is one reason why scientists are so interested in subsurface exploration, drilling, ground-penetrating radar, and eventually sample return missions that bring Martian soil and rock back to Earth for detailed analysis. Jurong was designed to operate for 93 Earth days. That was the mission's baseline expectation, the minimum amount of time engineers and scientists hoped the rover would survive on Mars. As it turned out, Jurong lasted much longer than that. It continued collecting data for 358 days, nearly 4 times its designed lifespan, before going dormant on May 20th, 2022. The rover was solar-powered, relying on panels to convert sunlight into electricity. Mars, being farther from the Sun than Earth, receives less solar energy. Dust storms can reduce that further, covering panels and blocking light. As Martian winter approached and dust accumulated, Zhurong's power levels dropped. The rover entered a dormant state, essentially hibernating, waiting for conditions to improve. Controllers expected Zhurong to wake up in December 2022, when spring returned to the southern hemisphere of Mars and sunlight increased. But the rover never re-established contact. The most likely explanation is that dust accumulation was more severe than anticipated, preventing the solar panels from generating enough power to revive the systems. This is the reality of exploring Mars. Rovers don't last forever. Dust is relentless. Temperatures fluctuate wildly, from relatively warm afternoons to bitterly cold nights that can freeze mechanisms and degrade electronics. Engineers designed for these conditions, but there are limits. Every mission ends eventually. And yet, in the time Zhurong was active, it sent back data that is still being analysed, still leading to new papers, still contributing to our understanding of Mars. The radar measurements it made beneath Utopia Planitia will be studied for years. They'll be compared with data from other missions, from orbiters, from future rovers, from sample return missions if those happen. Each piece of information adds to a larger picture. Planetary science is patient work. It unfolds over decades. The Viking landers touched down in 1976. The Curiosity rover has been exploring Gale Crater since 2012. Perseverance has been collecting samples in Jezero Crater since 2021, samples that won't return to Earth until the 2030s, if current plans hold. The Zhurong rover operated for less than a year, but the questions it raised will occupy scientists for far longer. At some point in Mars's history, the planet changed. It lost most of its atmosphere. Its magnetic field, which once shielded it from solar wind, weakened or disappeared. Without that protection, charged particles from the Sun stripped away atmospheric gases. Without a thick atmosphere, surface temperatures dropped. Water that had once flowed in rivers and pooled in lakes and oceans either evaporated into space or froze, some of it retreating into polar ice caps, some of it seeping into the ground and freezing there as permafrost. This transition didn't happen overnight. It took place over hundreds of millions of years, possibly longer. But the result was a planet that, for the past 3 billion years or so, has been cold, dry and hostile to life as we know it. If life did emerge on early Mars, it would have faced a gradually deteriorating environment. Perhaps it adapted, retreating underground, finding refuge in subsurface water, entering a kind of stasis. Perhaps it went extinct, unable to survive the changing conditions, or perhaps it never existed at all, and Mars remained a sterile world despite having many of the ingredients necessary for life. We don't know yet, and not knowing is part of what makes the search compelling. Each mission adds detail. Each instrument provides a new way of looking. Zhurong's radar showed us structures beneath the surface that orbital images couldn't reveal. Future missions will drill deeper, analyse more thoroughly, and perhaps bring samples back for study in laboratories here on Earth. But there's also something to be said for simply contemplating the possibility that another planet, not so different from our own in its early history, might have had oceans. That waves might have rolled across those oceans, driven by winds we'll never feel, under a sky lit by a sun that was younger and dimmer than the one we know. That life might have begun there, in tidal pools or along ancient coastlines, only to fade away as the planet grew cold. Earth's story and Mars's story are connected, not just because they're neighbours in the solar system, but because they both emerged from the same primordial material, the same cloud of gas and dust that collapsed to form the sun and planets. They both had volcanic activity, atmospheres, water, but their paths diverged. Earth remained warm and wet. Mars did not. Understanding why that divergence happened could tell us something important about planetary habitability in general. What factors determine whether a planet stays habitable over billions of years? How common are Earth-like worlds? How fragile are the conditions that allow life to persist? These aren't just academic questions. They shape how we think about our place in the universe, about what it means to be on a planet that is, as far as we know, uniquely suited to supporting complex life. They also inform the search for life elsewhere, around other stars in other solar systems, where planets we've never visited might be experiencing their own versions of the stories Earth and Mars have told. Mars has been a target of scientific interest for over a century. Early telescopic observations in the late 1800s led to speculation about canals and civilizations, ideas that captured public imagination but turned out to be based on optical illusions and wishful thinking. The first close-up images of Mars, taken by the Mariner missions in the 1960s, revealed a cratered, apparently lifeless surface. Early hopes for finding evidence of current life faded, but as more missions arrived, a different picture emerged. Mars wasn't just a dead rock, it had a complex geological history. The Viking landers in the 1970s tested Martian soil for signs of biological activity, with results that remain debated to this day. The Mars Global Surveyor, arriving in 1997, mapped the planet in unprecedented detail, revealing ancient valley networks and smooth plains that suggested water had once shaped the surface. The Mars exploration rovers, Spirit and Opportunity, found mineral evidence that water had interacted with rocks in specific locations. Curiosity discovered organic molecules and seasonal methane variations in Gale Crater. Perseverance is currently collecting samples from what may have been an ancient river delta. Each mission builds on what came before. Each uses new technology to ask questions that previous missions couldn't answer. Zhurong added to this lineage by providing ground-based subsurface data from a region that had only been studied from orbit. Its contribution is specific but significant, and the work continues. Planned missions include additional rovers, orbiters with more advanced instruments, and eventually the long-awaited Mars sample return. That mission, currently scheduled for the late 2030s or early 2040s, depending on budgets and technical challenges, would bring carefully selected Martian rocks and soil back to Earth. In laboratories here, scientists could perform analyses impossible to do remotely. They could look for isotopic signatures of biological processes, search for fossilized microbes, study the mineralogy and chemistry in exquisite detail. Sample return has been a goal of Mars exploration for decades. It's technically challenging, requiring a rover to collect and store samples, a lander to retrieve them, a rocket to launch them into Martian orbit, and a spacecraft to bring them back to Earth. Each step introduces complexity and risk, but the potential scientific reward is enormous. A few hundred grams of Martian material, analysed with the full suite of instruments available in terrestrial labs, could answer questions that rovers and orbiters can't. In the meantime, we work with what we have. And what Zhurong provided, even in its relatively short operational life, was a glimpse beneath the surface of a region suspected to hold evidence of ancient oceans. That glimpse, those 76 sloping reflectors captured by ground-penetrating radar, might represent some of the strongest evidence yet that Mars once had the kind of environment where life could have taken hold. It's difficult to reconstruct what an ancient Martian coastline would have actually looked like. We can make educated guesses based on the geology, but there's a lot we don't know. The colour of the water, for instance, depends on what was dissolved in it, what minerals were suspended as sediment, what kinds of microbes, if any, lived in it. The sky would have been different too. A thicker atmosphere might have scattered light differently, creating sunsets and sunrises unlike what we see on Mars today. The sun, being dimmer, would have provided less warmth and less light. Days would have been slightly shorter than Earth days, about 24.5 hours. The gravity, roughly 38% of Earth's, would have made waves behave differently, rising higher and moving more slowly than waves on Earth. Tides driven by Phobos and Deimos would have been gentler than Earth's moon-driven tides, but still present, still shaping the coastline over time. If you could have stood on that coastline assuming it existed, you might have felt wind, possibly strong if the atmospheric circulation patterns were vigorous. You might have seen sediment swirling in shallow water, darker patches where rivers fed fresh water into the ocean, litre areas where evaporation concentrated minerals. The shore itself might have been rocky in some places, sandy in others, depending on local geology. And if life existed, what would it have looked like? Almost certainly not anything you'd recognise as plants or animals. More likely microbial mats, thin layers of bacteria clinging to submerged rocks, perhaps greenish or reddish or brown depending on what pigments they use to capture energy from sunlight. Possibly biofilms, slimy coatings on pebbles where communities of different microbes cooperated or competed. Likely nothing you could see without a microscope, but even invisible life would have left traces, chemical byproducts, isotopic signatures, structures in sediment where mats trapped and bound particles together. These are the kinds of biosignatures scientists hope to find, not fossils of Martian fish or shells, but subtle chemical and physical clues that something was metabolizing, growing, reproducing. Finding such evidence, if it exists, will require going to the right places, and that's why the Zhurong discovery matters. If those sloping layers really do represent an ancient foreshore, then that region, or regions like it elsewhere on Mars, become prime targets for future exploration, not just for rovers, but for crewed missions if those happen, and for sample return missions that could bring material back for detailed study. One of the recurring themes in planetary science is that we're always working with incomplete information. We can't walk across Mars and examine every rock. We can't drill into every promising location. We can't bring back unlimited samples. Every mission has constraints, budget, mass limits on what can be launched, power availability, communication bandwidth, time. Rovers move slowly. Zhurong travelled at a maximum speed of about 200 meters per hour, though in practice it moved much slower, stopping frequently to take measurements, avoiding hazards, conserving power. In 358 days of operation, it covered a small area relative to the size of Utopia Planitia. The data it collected, while valuable, represents a tiny sample, and yet, from that tiny sample, researchers have drawn conclusions about an ocean that might have existed billions of years ago. How confident can we be in such conclusions? This is where the scientific process becomes important. The research team didn't just look at the radar data and announce they'd found a shoreline. They compared it to terrestrial analogues, to similar structures on Earth where the formation process is well understood. They considered alternative explanations, sand dunes, lava flows, and showed why those explanations didn't fit as well. They published their findings in a peer-reviewed journal, where other scientists could scrutinise their methods and interpretation. Some scientists will find the evidence compelling. Others will remain sceptical, pointing out ambiguities or suggesting alternative interpretations that the team didn't fully address. This is normal. It's how science works. New evidence doesn't immediately settle debates. It shifts the conversation, provides new data points, raises new questions. Over time, as more missions visit Mars, as we gather more data from different locations and different depths, the picture will become clearer. Perhaps future rovers will find additional evidence of shorelines in other regions. Perhaps sample return missions will bring back sediment with chemical signatures consistent with deposition in a coastal environment. Or perhaps alternative explanations will prove more convincing, and the structures Zhurong detected will turn out to be something else entirely. Certainty in planetary science is rare and hard-won. What we have instead is a gradually improving approximation of the truth, built up over decades of observations, experiments, and theoretical work. The Zhurong data adds to that approximation, and whether it ultimately convinces the broader scientific community will depend on how well it holds up under continued scrutiny. and how it integrates with future discoveries. If Mars did have oceans, and if those oceans covered significant portions of the planet's surface, then where did all that water go? This is one of the enduring mysteries of Martian science. Some of it is still there, frozen in the polar ice caps. Some is locked underground as permafrost, ice mixed with soil extending deep below the surface. Orbital measurements have detected vast deposits of subsurface ice, particularly in regions like Utopia Planitia. That ice represents a reservoir of water, but it's not enough to account for the volume that would have filled ancient oceans. Some water was lost to space. Mars's weak magnetic field and thin atmosphere left it vulnerable to solar wind, a stream of charged particles constantly flowing out from the sun. Over time, solar wind stripped away atmospheric gases, including water vapour. Hydrogen, a component of water, is light enough to escape Mars's gravity if it reaches the upper atmosphere. Oxygen, being heavier, would have been more likely to stay behind, possibly reacting with surface rocks to form iron oxides, the rust that gives Mars its red colour. This process, atmospheric escape driven by solar wind, has been observed by spacecraft like MAVEN, which orbits Mars specifically to study its upper atmosphere and how it interacts with the solar wind. MAVEN's measurements show that Mars is still losing atmosphere today, albeit slowly. Extrapolating backward, over billions of years, the cumulative loss could be substantial. But even accounting for ice caps, subsurface ice and atmospheric escape, the numbers don't quite add up. If Mars had oceans comparable in volume to Earth's, losing all that water would require more than what these mechanisms can explain. This suggests either that the oceans were smaller than some models predict, or that there are processes we don't fully understand yet. Climate modelling of early Mars remains an active area of research. Scientists build computer simulations that try to recreate the planet's ancient atmosphere, temperature, and hydrology. They adjust variables, atmospheric composition, solar luminosity, volcanic activity rates, and see whether the models can produce conditions consistent with the geological evidence. It's challenging work because small changes in assumptions can lead to very different outcomes. Some models suggest that Mars might have had a thicker atmosphere early in its history, thick enough to create a greenhouse effect that kept surface temperatures above freezing. Others suggest that warming might have been episodic, tied to volcanic activity or impacts. Still others explore the possibility that Mars was mostly cold, with brief melting events driven by changes in the planet's orbit. None of these models perfectly explains all the evidence. This is partly because Mars's early history was complex, and partly because we still have gaps in our knowledge. We don't know exactly what the ancient atmosphere was made of. We don't know how much volcanic activity occurred, or when. We don't know how the magnetic field changed over time, or how quickly the atmosphere was stripped away. The Zhurong discovery doesn't directly answer these questions, but it does provide a new piece of the puzzle. If the structures it detected are indeed ancient shoreline deposits, that tells us something about the stability of water in that region during a specific period of Mars's history. It suggests that at least locally, water persisted long enough to shape the landscape in recognizable ways. Searching for life beyond Earth requires a combination of patience, persistence, and careful reasoning. You can't just land on another planet and expect to immediately see something moving. Life, if it exists, or existed on Mars, is almost certainly microbial, small, simple, and probably extinct or at least dormant, buried underground where conditions are less harsh. The strategies for finding evidence of such life involve looking for biosignatures, chemical or physical traces that are difficult to explain without invoking biological processes. These might include organic molecules with structures that suggest they were produced by living organisms. Isotopic ratios that differ from what you would expect from purely geological processes, because living things preferentially use lighter isotopes of certain elements. Mineral deposits that form in the presence of microbial activity, like stromatolites or certain kinds of carbonate formations. or spatial patterns in sediment that suggest microbial mats or other biological structures. The challenge is that many biosignatures can also be produced by non-biological processes. Organic molecules can form abiotically through chemical reactions that don't involve life. Isotopic fractionation can result from geological processes. Mineral structures can mimic biological ones. This is why finding life, or proving it once existed, is so difficult. You need multiple lines of evidence that together make the biological explanation more compelling than the non-biological ones. Mars missions have been gradually building the capability to search for these biosignatures. Early missions focused on understanding the planet's basic geology and climate. Later missions started looking for signs of past water, because water is a prerequisite for life as we know it. Current missions are sampling materials from locations that might have been habitable, collecting data that could reveal chemical signatures of life. The ultimate goal is sample return, bringing Martian material back to Earth where it can be analysed with instruments far more sophisticated than anything that can be sent to Mars. A single rock sample, properly chosen, could contain layers of sediment deposited over millions of years, each layer potentially holding clues about the environment at the time it formed. But sample return is expensive and technically complex. It requires international cooperation, sustained funding over decades, and acceptance of the risks involved. The current plan, if it proceeds, wouldn't see samples returning to Earth until the late 2030s or early 2040s. That's a long time to wait for answers, and there's always the risk that budget constraints or technical challenges could delay or cancel the mission. In the meantime, scientists continue to work with the data they have. They refine their understanding of Mars's geology, climate and history. They identify promising locations for future exploration. They develop new instruments and techniques for detecting biosignatures, and they study extreme environments on Earth, places like Antarctica or deep-sea hydrothermal vents, where life persists under conditions once thought impossible, learning what kinds of signatures those organisms leave behind and how to recognise them. The search for life on Mars is in many ways a search for understanding about life in general. How does it start? What conditions does it require? How resilient is it? Can it adapt to changing environments, or does it inevitably go extinct when conditions deteriorate? These questions apply not just to Mars, but to Earth, and potentially to countless other worlds we haven't yet explored. 3.5 billion years is almost incomprehensibly long. Earth itself is only about 4.5 billion years old. Mars formed around the same time, coalescing from the same disk of material that gave birth to the Sun and all the planets. In the earliest era of the solar system, Mars and Earth weren't so different. Both were young, volcanic, hot, gradually cooling, developing atmospheres and surfaces that would bear little resemblance to what we see today. Life on Earth, as far as we can tell, appeared relatively quickly. The oldest fossils we've found, structures called stromatolites built by microbial mats, date back about 3.5 billion years. Chemical evidence suggests life might have existed even earlier, perhaps as far back as 3.8 or 3.9 billion years ago, shortly after the planet cooled enough for liquid water to exist on its surface. If Mars had liquid water during the same period, and if the chemistry there was similar to Earth's, then it's not unreasonable to think that life might have started on Mars too. The same organic molecules, the same energy sources, the same basic physics and chemistry. But something went wrong, or at least differently. Earth retained its magnetic field, kept most of its atmosphere, and remained habitable for billions of years. Mars lost its magnetic field, lost its atmosphere, and became the cold, dry planet we see today. Timing matters. If life emerged on Mars but the planet became uninhabitable within a few 100 million years, then Martian life, if it existed, might never have progressed beyond simple, single-celled organisms. It wouldn't have had time to evolve complexity, to develop multicellularity, to fill ecological niches the way life on Earth did. And if Martian life went extinct billions of years ago, then finding evidence of it requires searching through ancient rocks, looking for traces that have somehow survived the harsh conditions on the planet's surface. Radiation, temperature swings, oxidizing chemistry, all of these work to break down organic material. The best chance for preservation is probably underground, where rocks shield against radiation and where conditions are more stable. This is why missions like Zhurong, which carry ground-penetrating radar and can map subsurface structures, are so valuable. They give us a way to look beneath the surface without physically digging, to identify layers and features that might be worth investigating more closely in the future, and it's why scientists are so interested in locations like ancient coastlines. If life existed on Mars, shorelines are among the most likely places it would have thrived, and therefore among the most likely places to find evidence of it today. There's a certain quietness to Mars that comes through in the images sent back by rovers and landers. Empty plains stretching to the horizon, rocky outcrops casting long shadows in the thin light, dust devils spinning across flat expanses. No trees, no grass, no movement except the wind. It's the silence of a world where nothing grows, where no rivers flow, where the air is so thin that sound barely carries. And yet, beneath that silence, there's a kind of history, written in stone and sediment waiting to be read. Every rock on Mars is a record of the planet's past. Its composition tells you what minerals were present when it formed. Its texture tells you whether it cooled quickly or slowly, whether it was shaped by water or wind or volcanic heat. Its position tells you when it was deposited relative to other rocks in the same area. Layers stacked on top of each other, each one representing a different chapter in the planet's geological story. Reading that story requires patience and careful observation. Rovers move slowly, stopping to examine individual rocks, taking measurements, collecting data that gets transmitted back to Earth, where teams of scientists analyse it, debate its meaning, fit it into the larger picture they're building. The Zhurong rover, during its year of operation, added a few more pages to that story. It showed us structures beneath the surface that suggest water once shaped this landscape. It provided data that will be compared with findings from other missions, integrated into models of Mars's climate and geology, used to guide future exploration. And then it fell silent. As all missions eventually do, the dust accumulated, the solar panels darkened, the systems shut down, waiting for sunlight that never quite returned in sufficient strength. But the data remains, the radar profiles, the images, the measurements. They're archived, accessible to researchers now and in the future, ready to be reinterpreted as new theories emerge, as new context becomes available. This is how our understanding of Mars has grown over the decades, not through sudden revelations, but through the slow accumulation of data, the gradual refinement of ideas, the patient work of scientists who spend careers studying a planet they'll never visit. Mars is just one planet in one solar system, but the questions it raises apply far more broadly. If Mars had the potential for life but lost it, what does that tell us about how common habitable planets are? How stable do conditions need to be? How easily can a planet that starts out habitable become inhospitable? We know of thousands of planets around other stars now, detected through various methods over the past few decades. Some of them are in what's called the habitable zone, the range of distances from their star where liquid water could theoretically exist on the surface. But being in the habitable zone doesn't guarantee habitability. You also need the right kind of atmosphere, a magnetic field to protect against stellar wind, geological activity to recycle nutrients and regulate climate, and probably a dozen other factors we haven't fully identified yet. Mars shows us that even planets that start out with many of the right ingredients can end up lifeless. Earth shows us that under the right circumstances, life can not only emerge, but persist and diversify for billions of years. The difference between these two outcomes seems to depend on details we're still trying to understand. Size might matter. Mars is smaller than Earth, which means it cooled faster, lost its internal heat sooner, and couldn't maintain the kind of geological activity that keeps Earth's surface dynamic. Without that activity, Mars lost its magnetic field. Without the magnetic field, it couldn't protect its atmosphere from being stripped away by solar wind. Distance from the Sun clearly matters. Mars receives less solar energy than Earth, making it harder to maintain warm surface temperatures. But Venus, closer to the Sun than Earth, became a hellish greenhouse with surface temperatures hot enough to melt lead. So being in the habitable zone isn't enough. You also need the right atmosphere and climate feedbacks. The presence of a large moon might matter. Earth's moon stabilizes our planet's axial tilt, which in turn stabilizes our climate. Mars's 2 tiny moons don't provide that kind of stabilization. Over millions of years, Mars's tilt has varied much more than Earth's, causing dramatic climate swings. All of these factors interact in complex ways, and we're only beginning to understand how. Studying Mars helps, because it's close enough to investigate in detail, and because its history parallels Earth's in some ways while diverging dramatically in others. Every new piece of information about Mars, every new understanding of how its climate evolved or why it lost its water, informs our thinking about planetary habitability in general, and that in turn helps us think about the possibilities for life elsewhere. In our solar system, on moons like Europa or Enceladus that might have subsurface oceans. And beyond, on planets orbiting other stars, worlds we can't yet visit but can study from a distance, looking for signs of atmospheres, water, and maybe, someday, life. The future of Mars exploration depends on budgets, political priorities, technological capabilities, and a bit of luck. Sample return missions have been planned and replanned for years. The current timeline suggests samples might return to Earth in the late 2030s or early 2040s, but that assumes funding continues, technical challenges are overcome, and international cooperation remains stable. There's always the risk that a mission gets delayed or cancelled. Space exploration is expensive, and it competes with other priorities. When budgets get tight, science missions are often the first to be cut. The Mars Sample Return mission, which would involve multiple spacecraft launches, a rover on Mars, a lander with a rocket to launch samples into orbit, and a retrieval spacecraft to bring them back to Earth, is one of the most complex and expensive missions ever proposed. It's also one of the most scientifically valuable, but value doesn't always translate into sustained funding. In the meantime, other missions continue. The Perseverance rover is still operating in Jezero Crater, collecting samples and storing them in tubes that a future mission could retrieve. The Ingenuity helicopter, which was only supposed to fly 5 times, exceeded all expectations and demonstrated that aerial exploration of Mars is possible. Future missions might include more sophisticated helicopters or drones capable of covering larger areas and accessing locations that rovers can't reach. China has announced plans for its own Mars Sample Return mission, separate from the NASA ESA effort. If that proceeds on schedule, it could return samples in the early 2030s, potentially before the NASA mission. This introduces an element of competition, which historically has sometimes accelerated progress, though it also raises questions about international coordination and data sharing. Crewed missions to Mars remain aspirational. Various space agencies and private companies have proposed timelines, but the challenges are immense. Getting humans to Mars safely, keeping them alive during a months-long transit, supporting them on the surface for an extended stay, and bringing them back requires solving problems in life support, radiation protection, propulsion, and crew psychology that haven't been fully addressed yet. It will happen eventually, probably within this century, but predicting exactly when is difficult. Regardless of when or how humans eventually reach Mars, robotic exploration will continue to lead the way. Rovers and landers will identify interesting locations, test instruments and techniques, and build the knowledge base that future crewed missions will rely on. The data from missions like Zhurong, even though the rover itself is no longer active, contributes to that knowledge base and helps guide where future missions should go. The sloping structures Jurong detected beneath Utopia Planitia are intriguing but not definitive. They're consistent with the idea that this region once held water, that waves shaped the sediment, that a shoreline existed here billions of years ago. But consistency isn't proof. Other explanations, while less likely according to the research team's analysis, can't be completely ruled out. This is where future missions become important. If other rovers explore different parts of Utopia Planitia or other suspected ocean basins and find similar structures, that strengthens the case. If they don't, or if they find features that contradict the shoreline interpretation, that weakens it. Science progresses through this kind of iterative testing, where hypotheses are proposed based on initial evidence and then subjected to further scrutiny as more data becomes available. The advantage of the shoreline hypothesis is that it makes predictions. If these structures really are ancient foreshore deposits, then we should expect to find them at similar elevations in other parts of the basin. We should expect to find sediment sorting patterns, with finer material deposited farther from the proposed water source and coarser material closer. We should expect to find chemical signatures consistent with water deposition, certain minerals that form in wet environments. Testing these predictions will require time and resources, more missions, more instruments, more years of data collection. But that's the nature of planetary science. Answers come slowly, built up from accumulated evidence, refined through debate and reanalysis. And even if the structures Jurong found do turn out to be ancient shoreline deposits, that still leaves unanswered questions. How long did the water persist? Was it a true ocean, deep and stable, or more like a large lake that came and went over millions of years? What was the water's chemistry? Was it salty, fresh, acidic, alkaline? And most importantly, did it support life? These questions might not be answerable with rovers alone. They might require sample return, bringing actual Martian rocks and soil back to Earth, where they can be studied with the full range of analytical techniques available in modern laboratories. Only then might we be able to detect the subtle chemical or isotopic signatures that would indicate biological processes occurred in these ancient waters. There's something humbling about looking at images from Mars, seeing landscapes that no human has ever walked across, knowing that our understanding of this planet has been built entirely through machines we've sent to explore on our behalf, rovers with cameras and spectrometers and radar, moving slowly across dusty plains, stopping to examine rocks, sending data back across millions of kilometers of empty space. And there's something humbling about the timescales involved. 3.5 billion years since these potential shorelines formed. Longer than complex life has existed on Earth. Longer than most mountain ranges on our planet have stood. A span of time so vast that it's difficult to grasp emotionally, even if we understand it intellectually. Mars has been silent for most of that time. If it ever had rivers flowing and waves breaking on shorelines, those sounds faded billions of years ago. The planet's voice, if it can be said to have had one, went quiet when its atmosphere thinned and its water disappeared. But the silence isn't complete. The rocks still speak in their way. The geological record preserves information about what happened, even if interpreting that information requires sophisticated instruments and careful analysis. Every layer of sediment, every mineral composition, every subtle structure detected by ground-penetrating radar is a word in a language we're slowly learning to read. The Jurong rover added a few sentences to that text. It showed us slopes beneath the surface that might record the interaction of water and sediment over geologically significant periods. It provided data that, when combined with observations from other missions, helps us piece together a more complete picture of what Mars once was. And that picture, still incomplete and subject to revision, suggests a world that was once more dynamic and possibly more hospitable than the frozen desert we see today. A world where water-shaped landscapes, where chemistry unfolded in ways that might have given rise to life, where conditions existed that, on Earth, led to the emergence and diversification of organisms that eventually produced forests and oceans, and, eventually, minds capable of wondering about other worlds. Whether Mars followed a similar path, or whether it remained barren despite having many of the necessary ingredients, is something we're still trying to determine. The evidence leans toward the possibility that Mars was habitable, at least for a while, at least in some regions. But possibility isn't certainty, and habitable doesn't necessarily mean inhabited. The search continues, patient and methodical, driven by curiosity about our place in the universe, and by the hope that we might not be alone, that life might have emerged more than once, in more than one place, even if that other place is now cold and silent. One of the lessons Mars teaches is that habitability is fragile. A planet can start with the right ingredients, water, organic molecules, energy sources, and still end up lifeless. The factors that make a world habitable, a thick enough atmosphere, a strong enough magnetic field, stable enough climate, aren't permanent. They can change, sometimes gradually over billions of years, sometimes more rapidly in response to catastrophic events. Earth has had its own close calls, the Snowball Earth episodes, when ice covered most or all of the planet's surface. The Great Oxygenation Event, when photosynthetic organisms began producing oxygen as a waste product, poisoning many existing life forms and fundamentally altering the atmosphere. Mass extinctions that wiped out large percentages of species. Yet life persisted, adapted, evolved. Mars apparently wasn't so fortunate, or perhaps its trajectory was simply different from the start. Whatever the reason, it went from a planet with liquid water and possibly life to the frozen desert we observe today. And it did so relatively early in solar system history, leaving billions of years during which the planet has been essentially static, at least on its surface. Could Earth follow a similar path? Not in exactly the same way. Earth is larger, retains its magnetic field, and has geological activity that should continue for billions of years. But the sun is gradually brightening, and in a billion years or so, Earth will receive enough additional solar energy that the oceans will begin to evaporate. Eventually, perhaps in 2 or 3 billion years, Earth will become too hot for liquid water to exist on its surface. At that point, it will be as uninhabitable as Mars is now, though for opposite reasons. So in the very long term, all planets in the habitable zone will eventually leave it, either because the star they orbit changes or because the planet itself changes. Habitability is temporary, measured in billions of years perhaps, but still finite. This makes the question of life's emergence more interesting. If habitable conditions are temporary, does life need to emerge quickly to take advantage of the window of opportunity? Earth's geological record suggests life appeared relatively soon after the planet cooled enough for liquid water, within a few 100 million years at most. Was this luck, or is life something that emerges readily whenever conditions are right? If Mars had habitable conditions for a few 100 million years early in its history, was that long enough for life to start? And if life did start, could it have left traces that we could still detect billions of years later? These questions don't have answers yet, but they frame the search for life on Mars in a particular way. We're not just looking for life that exists now, we're looking for evidence of life that might have existed long ago, in an environment very different from the one we see today, and we're trying to determine whether that evidence could have survived the harsh conditions that have prevailed since. It's a difficult task, like trying to find a fossil of a single-celled organism in rocks that have been baked, frozen, irradiated and chemically altered for billions of years. But it's not impossible, and the potential reward, confirming that life emerged independently on another planet, justifies the effort. Scientific understanding doesn't progress smoothly. It moves in fits and starts, with periods of rapid advancement followed by slower periods of consolidation and refinement. Mars exploration has followed this pattern. The early Mariner missions provided the first close-up views and revealed a cratered surface that looked superficially moon-like. Viking landers added detail but raised as many questions as they answered. A gap in successful missions during the 1990s was followed by a renaissance beginning with Mars Global Surveyor, and continuing through the rovers and orbiters we have today. Each successful mission builds capabilities that enable the next one. Early orbiters mapped the planet's topography, identifying regions of interest. Landers tested technologies for entering the Martian atmosphere and touching down safely. Rovers demonstrated that mobile platforms could survive and function on the surface for extended periods. Helicopters proved that aerial vehicles could operate in Mars's thin atmosphere. The Zhurong mission fit into this progression by demonstrating China's capability to land and operate a rover on Mars, joining the small group of nations that have achieved this. Its contributions to science, particularly the subsurface radar data, added new information that will be integrated with findings from other missions, and the next phase, sample return, will represent another step forward. Instead of analysing Martian material with instruments constrained by mass and power limits, scientists will have access to state-of-the-art laboratories with no such restrictions. They'll be able to perform experiments that take weeks or months, using techniques that can't be miniaturized for spaceflight. But sample return is still years away, and even once samples arrive on Earth, analysing them will take time. Martian rocks aren't just going to yield their secrets immediately. They'll need to be carefully examined, their chemistry and mineralogy mapped in detail, their age determined through radiometric dating, their structure studied under microscopes and with spectroscopic instruments, and all of that work will lead to papers published in scientific journals, to conferences where researchers debate interpretations, to revisions of theories as new data challenges old assumptions. The process is slow, often frustratingly so, but it's also thorough, designed to filter out errors and converge gradually on the truth. The structures Zhurong detected will be one piece of this larger puzzle. They'll be compared with data from future missions, integrated into models of Mars's ancient geography, used to refine estimates of how much water the planet once held and where it went. And someday, maybe decades from now, we'll have a fairly complete picture of Mars's early history. We'll know whether it had oceans or just large lakes. We'll understand its climate during the period when water was stable on the surface. We'll know whether life emerged there, or at least whether conditions were conducive to it. That future understanding is being built now, one mission at a time, one dataset at a time, through the patient work of scientists and engineers who might not live to see the final picture completed, but who contribute essential pieces to it nonetheless. Not every question has an answer yet. Some might never have definitive answers, depending on how well the geological record has been preserved and how thoroughly we are able to search it. The Zhurong data suggests that Mars once had conditions that resemble those of terrestrial coastlines. The sloping structures detected by radar fit the pattern of ancient foreshore deposits, but suggests and fit the pattern aren't the same as proves. There's still room for interpretation, still the possibility that future data will lead to different conclusions. This is where science requires a certain tolerance for ambiguity. Not everything can be known immediately. Some questions take decades to answer, and some answers remain provisional, subject to revision as better data becomes available. For now, what we can say is that Mars had water early in its history. The evidence for this is strong, coming from multiple independent sources. Minerals that form in the presence of water, erosion patterns consistent with flowing water, ice detected at the poles and underground, and now potentially structures that suggest standing water shape the landscape in specific locations. We can also say that Mars lost most of its water, though we don't fully understand all the mechanisms involved or the exact timeline. Some was lost to space, some froze and remains in ice caps and permafrost. Some might be chemically bound in minerals. We can say that if Mars had habitable conditions, they existed primarily early in the planet's history, during a period that ended somewhere between 3 and 4 billion years ago. After that, the planet became increasingly hostile to life as we know it, though isolated habitable niches might have persisted underground. And we can say that finding definitive evidence of past life on Mars, if such evidence exists, will likely require bringing samples back to Earth for detailed analysis. Rovers and landers can do impressive work, but they have limitations. Some questions need laboratory conditions to answer. Beyond that, much remains uncertain. And that uncertainty, rather than being a failure of science, is simply an acknowledgement of how much there is still to learn. Mars has been studied intensively for decades, yet it continues to surprise us, to challenge our models, to reveal complexity we didn't anticipate. The journey toward understanding this planet is ongoing, and missions like Zhurong contribute to it in ways both large and small. The data they provide might not answer every question, but it moves the conversation forward, adds detail to the picture we're building, and helps guide future exploration toward locations where answers are most likely to be found. And sometimes, in the quiet moments between discoveries, it's enough to simply contemplate what we've learned so far, that Mars was once more Earth-like than we imagined. That water shaped its surface in ways we're only beginning to understand. That the history of our solar system is more complex and interesting than early observation suggested. And that the search for life, wherever it might have existed, is a search worth continuing, even when the answers are elusive and the timescales are measured in decades or longer. The ancient shoreline, if that's what Zhurong found, is silent now. But in that silence, there's still information, still stories waiting to be read in the rock and sediment. And the work of reading those stories, of piecing together what Mars once was and what it might tell us about life in the universe, continues. When we think about ancient shorelines on Mars, we're really thinking about memory. Not memory in the biological sense, but geological memory. The way rocks and sediment preserve information about events that happened billions of years ago. Every layer tells a story about the conditions when it was deposited. The size of the grains reveals something about the energy of the environment. Fine silt settles in calm water. Coarse sand and pebbles require stronger currents or wave action to move and deposit. The angle of deposition matters too. Horizontal layers typically form in quiet environments like lake bottoms or deep ocean floors, where sediment drifts down through still water and accumulates evenly. Sloping layers, like those Zhurong detected, form in more dynamic settings. A beach slope records the back and forth of waves, the rise and fall of tides, the gradual building up of material in a zone where water meets land. On Earth, geologists can examine these structures directly. They can dig into beach deposits, extract cores, take samples back to laboratories for detailed analysis. They can measure the orientation of individual grains, looking for patterns that indicate which direction the waves came from or how strong the currents were. They can analyse the mineral composition to determine what kind of rocks were being eroded upstream, where the sediment originated. On Mars, we can't do most of that yet. What we have instead are indirect measurements, radar signals that bounce off boundaries between layers but don't tell us much about the fine details. Images from orbit that show large-scale patterns but lack the resolution to see individual grains. Data from rovers that sample tiny fractions of the landscape, providing snapshots rather than comprehensive surveys. And yet, from these limited observations, a picture emerges. The Bay of Bengal comparison that the Zhurong team made isn't arbitrary. The Bay of Bengal shoreline has been studied extensively. Scientists understand how its beach deposits formed, what processes shaped them, how they relate to sea level changes and sediment supply from rivers. When they see similar patterns in the Martian radar data, similar angles and layer configurations, it suggests similar processes might have been at work. This is how planetary geology often works. You find something on another world that looks familiar, and you use your understanding of how such features form on Earth to interpret what you're seeing. It's not perfect. Mars isn't Earth. Gravity is different. The atmosphere was different. The water chemistry might have been different, but the fundamental physics is the same. Water flowing downhill, waves breaking on a shore, sediment settling out of suspension. These processes follow the same rules regardless of which planet they occur on. The Zhurong data adds to a growing body of evidence that Mars once had environments similar to those on Earth. Not identical, but similar enough that terrestrial analogues are useful for understanding them. And that similarity is important, because it means that if we want to know where life might have emerged on Mars, we can look to the places on Earth where life thrives, and use those as guides. Shorelines on Earth are biologically productive. The intertidal zone, where land meets sea, supports an abundance of life adapted to conditions that change with the tides. Organisms that can tolerate being submerged part of the time and exposed to air at other times. Communities that take advantage of nutrients brought in by rivers and stirred up by wave action. If Mars had similar environments, even for a relatively brief period in geological terms, they might have been among the most favourable places for life to begin. One of the challenges in searching for evidence of ancient life on Mars is that 3.5 billion years is a long time for organic material to survive. On Earth, fossils from that era are rare and often controversial. The oldest widely accepted fossils are stromatolites, layered structures built by microbial mats. They survive because they're made of rock, mineral deposits precipitated by the metabolic activity of microbes. The microbes themselves are long gone, but the structures they built remain. Finding similar structures on Mars would be compelling evidence for past life. But it would also require looking in the right places and recognizing them for what they are. Stromatolites can sometimes be difficult to distinguish from abiotic mineral formations, structures that look biological but form through purely chemical processes. This has led to debates about some of Earth's oldest fossils, with scientists disagreeing about whether certain structures are truly biological in origin. On Mars, the challenge is compounded by the fact that we can't examine potential fossils in person. We rely on images and spectroscopic data from rovers, which have limited resolution and can't perform all the tests that would be done in a laboratory. A structure that looks like it might be a stromatolite could also be a mineral deposit formed by evaporation or crystallization. Without detailed chemical analysis, it's difficult to tell the difference. This is one reason why sample return is so important. Bring the rocks back to Earth, and you can study them with the electron microscopes, mass spectrometers, and other instruments that can detect subtle chemical signatures of biological activity. You can look for patterns in carbon isotope ratios, since living organisms preferentially use lighter isotopes of carbon, leaving a distinctive signature. You can search for complex organic molecules that are difficult to produce abiotically. You can examine the microscopic structure of minerals to see if they show evidence of having formed in the presence of microbial activity. But even with all these tools, proving that something is a fossil, rather than a look-alike formed by non-biological processes, is challenging. Science requires extraordinary evidence for extraordinary claims, and the claim that life existed on another planet is about as extraordinary as it gets. Multiple independent lines of evidence would be needed, all pointing toward the same conclusion, before the scientific community would broadly accept that life once existed on Mars. The shoreline deposits Zhurong detected, if they are indeed shoreline deposits, don't directly tell us whether life existed. But they tell us where to look. Coastal environments, places where water was stable enough for complex chemistry to unfold over extended periods, are prime targets. If we're going to send future missions to search for biosignatures, knowing where ancient coastlines were located helps us prioritize landing sites. And there's another consideration. Even if we don't find direct evidence of life, understanding Mars's past environments tells us something important about planetary habitability in general. It tells us what conditions existed, whether they were suitable for life, and how long they persisted. This information is valuable even in the absence of confirmed biosignatures, because it helps us understand the range of conditions under which life might arise and the factors that determine whether a planet remains habitable over geological timescales. Mars operates on different timescales than Earth in some ways, and similar ones in others. A Martian day, called a sol, is about 24 hours and 37 minutes, remarkably close to an Earth day. This similarity made it easier to design solar-powered rovers, since the day-night cycle is familiar and the patterns of sunlight are predictable. But a Martian year is nearly twice as long as an Earth year, 687 Earth days, because Mars takes longer to orbit the Sun. This means seasons on Mars last longer, with each season stretching for several Earth months. The planet's axial tilt, similar to Earth's, creates seasons, but the longer year means those seasons unfold more slowly. Mars also has a more eccentric orbit than Earth, meaning its distance from the Sun varies more over the course of a year. This creates more extreme seasonal differences, particularly in the southern hemisphere. Southern summer, when Mars is closest to the Sun, is shorter and warmer than northern summer. Southern winter, when Mars is farthest from the Sun, is longer and colder than northern winter. These orbital characteristics affect the planet's climate in subtle ways. They influence wind patterns, dust storm frequency, and the sublimation and deposition of carbon dioxide ice at the poles. Over longer timescales, changes in Mars's orbit and axial tilt create climate cycles similar to the Milankovitch cycles that drive ice ages on Earth. Every few 100,000 years, Mars's tilt changes significantly, altering how much sunlight different latitudes receive and potentially causing ice to migrate from the poles toward the equator or vice versa. These cycles might have been important in Mars's ancient past. If the planet's climate was borderline for liquid water, small changes in orbital parameters could have tipped it one way or the other. Periods of higher obliquity, when the tilt was greater, might have brought warmer summers that melted ice and created temporary lakes or seas. Periods of lower obliquity might have plunged the planet into deep freezes. The evidence we see today, valley networks, crater lakes, and potentially coastlines, might represent snapshots from times when orbital conditions favoured melting. Or they might represent a longer-term climate state that eventually gave way to the cold, dry conditions we see now. Distinguishing between these possibilities requires understanding the timing of different geological features, which in turn requires radiometric dating of rocks, something we can only do with samples returned to Earth. This is where patience becomes essential. We can't rush the process of understanding Mars. Each mission provides pieces of the puzzle, but fitting those pieces together takes time. Zhurong operated for less than a year, but the data it collected will be analysed for years. Scientists will compare it with data from other missions, integrate it into climate models, use it to test hypotheses about how Mars evolved. And slowly, incrementally, the picture becomes clearer. Not complete, perhaps never complete, but clearer. We learn which ideas are consistent with the evidence, and which need to be revised or abandoned. We develop better questions to ask and better ways to answer them. We move closer to understanding what Mars was, and what it might tell us about the possibilities for life beyond Earth. One of the interesting aspects of searching for life on Mars is that it requires thinking about geology and biology together. On Earth, these are often treated as separate disciplines, but in the context of ancient Mars, they are inseparable. Life, if it existed on Mars, would have been intimately connected to the planet's geology. Microbes would have lived in water that was in contact with rocks. Their metabolism would have been driven by chemical reactions involving minerals. They might have precipitated minerals as byproducts of their metabolism, creating deposits that change the composition of the sediment they lived in. This is why biosignatures are so often chemical or mineralogical. We look for patterns in rock composition that are difficult to explain without invoking biology. On Earth, banded iron formations, massive deposits of iron oxide that formed in ancient oceans, are thought to record the rise of oxygen-producing photosynthetic organisms. The oxygen produced by these microbes reacted with dissolved iron in seawater, causing it to precipitate and accumulate on the ocean floor. On Mars, we might find similar signatures. Not necessarily banded iron formations, since Mars's ocean chemistry would have been different from Earth's, but other mineral assemblages that suggest biological activity. Carbonates, for instance, can form biologically or abiotically, but the details of their crystal structure and isotopic composition can sometimes distinguish between the two origins. The challenge is that Mars's surface has been heavily altered since the time when water was abundant. Weathering, erosion, impacts, and oxidation have all modified the rocks we see today. Any biosignatures that once existed on the surface have likely been degraded or destroyed. This is why the focus has shifted to subsurface exploration and to finding rocks that have been less exposed to the harsh surface conditions. The subsurface is more stable, temperatures don't fluctuate as much, radiation doesn't penetrate as deeply, chemical weathering proceeds more slowly. If organic material or other biosignatures were preserved anywhere, the subsurface is where they're most likely to still exist. This is what makes Zhurong's ground-penetrating radar data valuable. It gives us a window into the subsurface without requiring us to dig. We can see layering, identify depth to different geological units, and prioritize locations that might be worth drilling into or sampling more intensively in the future. And it's why the potential identification of ancient shoreline deposits is exciting. If those deposits are where the radar data suggests they are, 10 to 35 metres below the surface, they're deep enough to have been protected from the worst of the surface weathering, but potentially accessible to future drilling missions. A drill capable of reaching that depth could retrieve samples that have been shielded from radiation and oxidation for billions of years, samples that might preserve information about Mars's ancient environment and possibly even traces of ancient life. Studying Mars isn't just about understanding Mars, it's about understanding planets in general. Comparative planetology, the practice of studying multiple planets to understand the principles that govern their formation and evolution, has become increasingly important as we've discovered more about our solar system and about planets around other stars. Earth, Venus and Mars all formed from the same protoplanetary disk, all started with similar compositions, and all went through similar early stages of development. But they ended up very different. Venus became a hellish greenhouse with surface temperatures hot enough to melt lead. Earth remained temperate and developed a biosphere that has persisted for billions of years. Mars became cold and dry, losing most of its atmosphere early in its history. Understanding why these three planets diverged helps us understand what factors are most important for habitability. Size matters. Mars is smaller and cooled faster. Distance from the Sun matters. Venus is too close. Mars is too far. Atmospheric composition and dynamics matter. Venus's thick atmosphere created a runaway greenhouse, while Mars lost its atmosphere to space. But there are also subtleties we're still trying to understand. Why did Mars lose its magnetic field so early? Was it simply because the planet cooled and its core solidified, or were there other factors? Did Mars have plate tectonics early in its history, and if so, why did they stop? How did the loss of the magnetic field affect atmospheric loss? And could Mars have retained its atmosphere longer if the magnetic field had persisted? These questions are relevant not just to Mars, but to exoplanets, planets orbiting other stars that we can observe but not yet visit. When astronomers detect a rocky planet in the habitable zone of a distant star, they want to know whether it's more like Earth or more like Mars. Is it a world with oceans and possibly life, or is it a frozen desert? Understanding Mars helps us make educated guesses about those distant worlds. The Zhurong discovery fits into this broader context. If Mars had stable bodies of water for extended periods, that tells us something about the resilience of habitable conditions even on planets that eventually become inhospitable. It suggests that windows of habitability might be common in planetary evolution, even if permanent habitability is rare. And it raises questions about whether life, given such a window, is likely to emerge. On Earth, life appeared relatively quickly once conditions were suitable. Does that mean life emerges readily whenever the conditions are right, or was Earth lucky? If Mars had similar conditions and we find no evidence of life, what does that tell us about the probability of abiogenesis, the origin of life from non-living matter? These are questions that reach beyond Mars, beyond our solar system, into the realm of astrobiology and the search for life throughout the universe. Every new piece of information about Mars contributes to this larger inquiry, helping us understand not just one planet's history, but the general principles that govern life and habitability. Scientific progress is rarely dramatic. Textbooks and documentaries sometimes give the impression that discoveries happen suddenly, that one observation or experiment immediately overturns previous understanding and establishes new truth. But that's not usually how it works. More commonly, understanding accumulates gradually. A hypothesis is proposed based on limited evidence, more data is collected, and the hypothesis is refined. Alternative explanations are considered and evaluated. Debates unfold at conferences and in journal articles. Slowly, a consensus emerges, not because one side wins an argument decisively, but because the weight of evidence gradually shifts in one direction. The question of whether Mars had oceans has been following this pattern for decades. Early suggestions based on features visible in orbital images were met with skepticism. The features could be explained other ways, and there wasn't enough data to rule out alternative explanations. As more missions arrived and more data accumulated, the evidence for past water became stronger. Minerals that form in water were found. Valley networks were mapped in detail. Crater lakes were identified, but oceans remained controversial. Shorelines visible from orbit could be interpreted differently depending on assumptions about erosion and geological history. Some features thought to be beaches might have been formed by processes unrelated to standing water. The debate continued, with scientists on both sides publishing papers supporting their interpretations. Zhurong's data doesn't definitively settle the debate, but it adds a new kind of evidence, subsurface radar profiles showing structures consistent with coastal deposition. This is harder to explain away than orbital images of surface features. It provides detail that complements and reinforces other lines of evidence. Over time, as more missions collect more data, the balance of evidence shifts. It becomes increasingly difficult to explain all the observations without invoking substantial amounts of liquid water on ancient Mars. The question shifts from did Mars have water to how much water and for how long. This is progress, even if it's not as dramatic as a sudden breakthrough. It's the slow, steady work of narrowing the range of uncertainty, eliminating hypotheses that don't fit the data, and converging on explanations that account for all the observations. And this progress happens in increments. A single mission, a single data set, a single paper rarely changes everything. But each contributes to the larger edifice of understanding. The Mariner mission showed us what Mars looked like. Viking tested for signs of current biological activity. Mars Global Surveyor mapped the planet's topography. Spirit and Opportunity found evidence of past water in specific locations. Curiosity discovered organic molecules. Perseverance is collecting samples for future return. Zhurong mapped subsurface structures in Utopia Planitia. Each of these missions added something. Together they've transformed our understanding of Mars from a seemingly dead, uninteresting world to a planet with a complex history that might have supported life. That's progress, even if no single mission could claim to have made the complete discovery on its own. There's something almost meditative about thinking about geological timescales. 3.5 billion years is so far beyond human experience that it becomes abstract, a number without immediate emotional weight. But if you sit with it long enough, let it settle in your mind, it begins to evoke a kind of quiet wonder. 3.5 billion years ago, Earth had no complex life. No plants, no animals, nothing visible to the naked eye. Just microbes, single-celled organisms living in oceans and possibly on land, slowly changing the planet's chemistry. The continents were smaller and arranged differently. The atmosphere had much less oxygen. The moon was closer, and tides were stronger. And on Mars, if the evidence is correct, there was water. Rivers flowing through valleys, depositing sediment, lakes forming in impact craters, possibly an ocean covering low-lying northern plains, its shoreline shaped by waves and tides. The planet was warmer, its atmosphere thicker, conditions closer to being hospitable to life. But over hundreds of millions of years things changed. Mars's magnetic field weakened or disappeared. Without that protection, solar wind began stripping away the atmosphere. As the atmosphere thinned, surface temperatures dropped. Water that had been liquid began to freeze or evaporate. Rivers stopped flowing. Lakes dried up. The ocean, if it existed, either froze solid or evaporated away, its water escaping to space or seeping into the ground. This transformation didn't happen quickly by human standards. It probably took tens or hundreds of millions of years, time enough for thousands of human civilizations to rise and fall, if humans had existed then. But in geological terms, it's a relatively brief chapter. Mars went from potentially habitable to definitely inhospitable in what amounts to a blink on the planetary timescale. And then, for the next 3 billion years or so, Mars has been essentially as we see it today. Cold, dry, dust storms occasionally sweeping across the surface, ice caps waxing and waning with the seasons, but fundamentally static. No rivers carving new valleys, no oceans depositing new layers of sediment, just wind and occasional meteorite impacts, slowly eroding and rearranging the surface. The structures Jurong detected, those sloping layers buried 10 to 35 metres down, have been sitting there for most of that time, covered by later deposits, protected from the harshest surface conditions, waiting for someone to come along with ground-penetrating radar and notice them. It's a strange thought. That evidence of ancient shorelines could remain hidden but intact for billions of years. That information about what Mars once was could persist, even as the planet itself changed beyond recognition. And stranger still that we, products of evolution on a completely different planet, could develop the technology to travel to Mars, send instruments beneath its surface, and begin to reconstruct its ancient history. There's something humbling about it. We live such brief lives, a century at most, barely enough time to witness significant changes in our own planet's climate, let alone geological transformations. But through science, we can reach back across billions of years, read stories written in rock, and piece together narratives about worlds we'll never see as they once were. This is part of what makes planetary science compelling. It's not just about collecting data or testing hypotheses. It's about connecting with deep time, with scales of change that dwarf human history, with questions about origins and endings that touch on something fundamental about existence. Mars was once different. It might have had life. It lost its habitability. And now, billions of years later, we're trying to understand what happened, not just for curiosity's sake, but because the story of Mars might inform our understanding of our own planet's future, of other planets throughout the galaxy, of the conditions that allow life to emerge and persist. One of the uncomfortable truths that Mars confronts us with is that habitable conditions don't last forever. Planets change, stars evolve. Nothing is permanent on cosmic timescales. Earth has been habitable for billions of years, long enough for life to evolve from single-celled organisms to the complex biosphere we see today. But this won't continue indefinitely. The sun is gradually brightening as it ages. In 1 billion years, maybe less, Earth will receive enough additional solar energy that the oceans will begin to evaporate. Water vapour is a greenhouse gas, so as more water enters the atmosphere, temperatures will rise further, causing more evaporation in a runaway process. Eventually, Earth will lose its oceans. The hydrogen from water molecules will escape to space, just as it did on Mars. The planet will become too hot for life as we know it. This is billions of years in the future, an unimaginably long time by human standards, but it's as inevitable as the sun rising tomorrow. Mars shows us what the endpoint of such a process might look like. A planet that once had water, that might have supported life, transformed into a cold desert where nothing grows and nothing moves except dust stirred by wind. It's a sobering reminder that the conditions we depend on are temporary features of a particular moment in planetary evolution. But there's also something oddly peaceful about this perspective. The timescales are so vast that they remove any sense of urgency. Earth's habitability isn't in immediate danger from solar evolution. We have 1 billion years, give or take. Humanity, if it survives that long, will have had time to develop technologies we can't currently imagine. possibly even methods for migrating to other star systems or engineering planetary climates. And on shorter timescales, the timescales that matter to human civilization, Earth remains resilient. The climate can change and is changing due to human activity, but the planet itself will persist. Life will adapt, as it always has. The question isn't whether Earth will continue to exist, but whether the conditions humans depend on will remain stable. Mars, in its current state, represents one possible future, but not an inevitable one for Earth, at least not on timescales humans need to worry about. It's a reminder of planetary fragility, yes, but also of the fact that Earth has remained habitable for an extraordinarily long time despite all the things that could have gone wrong. Understanding Mars's history helps us understand this. It shows us what factors determine whether a planet stays habitable. Size matters, magnetic fields matter, orbital position matters, atmospheric composition and retention matter. But also, there's an element of contingency, of specific events and circumstances that unfold differently on different worlds. Mars lost its magnetic field early, probably because its core solidified as the planet cooled. Without the magnetic field, atmospheric loss accelerated. But would a slightly larger Mars have retained its heat longer, kept its magnetic field active and remained habitable? Possibly. Would Earth, if it were smaller or farther from the Sun, have followed a similar trajectory? Maybe. These questions don't have definitive answers, but they frame how we think about planetary habitability. They remind us that Earth's long-term habitability is the result of many factors aligning favourably, and that this alignment isn't guaranteed for every rocky planet in every habitable zone. And they give us context for thinking about the search for life elsewhere. If habitability is often temporary, if many planets go through brief habitable periods early in their history and then become inhospitable, then looking for current life on exoplanets might be difficult. We might be more likely to find evidence of past life, or to find planets that are currently habitable but won't remain so. Mars in this sense isn't just a case study in what happened to one particular planet. It's a window into the broader patterns of planetary evolution. Patterns that play out throughout the galaxy on worlds we'll never visit, but can try to understand from a distance. The search for life on Mars has been ongoing for decades now, and in all that time we haven't found definitive evidence. No fossils, no chemical signatures that unambiguously point to biology, no structures that can only be explained as remnants of living organisms. This could mean life never existed on Mars, or it could mean we haven't looked in the right places yet, or with the right instruments, or with sufficient thoroughness. Either possibility is interesting. If Mars was habitable but remained sterile, that tells us something important about how difficult it is for life to begin. Earth might have been fortunate, or there might be some ingredient necessary for a biogenesis that Mars lacked despite having water and organic molecules. If Mars did have life but we haven't found evidence yet, that tells us something about the challenge of detecting ancient biosignatures, especially on a planet that has been geologically inactive for billions of years. It suggests that finding evidence of extinct life elsewhere in the universe will be difficult, requiring careful selection of where to look and sophisticated techniques for distinguishing biological from non-biological signatures. The Jurong discovery doesn't answer the question of whether life existed, but it helps us think about where we should look. If the structures it detected really are ancient coastal deposits, then that region is a place where conditions favoured the kinds of chemistry that might lead to life. Future missions could target similar locations, drilling into subsurface layers that have been protected from radiation and weathering, searching for organic molecules or isotopic signatures or mineral formations that would be difficult to explain without invoking biology. But even if those future missions find nothing, the search itself is valuable. Every location we examine and find sterile narrows the range of possibilities. Every rock we analyse and find devoid of biosignatures gives us more information about what Mars was like and what processes shaped it. Negative results are still results, still data points that contribute to our understanding. And there's something to be said for the act of searching itself, for the patience and persistence required to explore a planet so thoroughly that we can be confident in our conclusions, positive or negative. Science isn't always about making dramatic discoveries. Sometimes it's about doing the careful, methodical work of ruling things out, of showing that if something exists, it's not here, or it's rarer than we thought, or it's preserved in ways we haven't yet figured out how to detect. Mars has taught us patience. It's taught us that questions worth answering often take decades to resolve. That understanding comes from accumulated evidence, not single observations. That certainty is hard-won and often elusive, and it's taught us humility. Every time we think we understand the planet, it surprises us. Features that looked simple from orbit turn out to be complex when examined up close. Processes we thought we understood reveal unexpected subtleties. Questions we thought were answered raise new questions that we hadn't anticipated. The potential ancient shoreline in Utopia Planitia is just the latest example. It adds to our understanding, but it also raises new questions. How extensive was this body of water? How long did it persist? What was its chemistry? Did it connect to other water bodies elsewhere on the planet? And most importantly, did it support life? These questions will take time to answer. Some might never be fully answered. But the process of trying to answer them, of sending missions and collecting data, and refining our understanding is itself worthwhile. It's how we learn. It's how science progresses. It's how we gradually build up a picture of the universe that's more accurate and more complete than what we started with. Utopia, Planitia, today is quiet in a way that's difficult to convey. Images from orbit show a vast, nearly featureless plain, interrupted only by scattered craters and subtle variations in texture. Close-up views from the surface reveal rocks and dust stretching to the horizon beneath a pale pink sky. There is no flowing water, no vegetation, no movement, except for the slow crawl of a rover leaving faint tracks behind it. A landscape defined almost entirely by stillness. The name Utopia Planitia means Plains of Paradise, an ironic title given the region's present condition. It was chosen long before spacecraft could see Mars in detail, when astronomers mapped light and dark regions through telescopes and gave them evocative names based on imagination rather than geology. What we now know is that Utopia Planitia is an immense impact basin, formed billions of years ago when a massive object struck Mars at extraordinary speed. The collision excavated a depression more than 3,000 kilometers across, making it one of the largest impact structures in the solar system. Over time, erosion and deposition softened its edges. Sediment carried by wind and possibly by water slowly filled the basin. The dramatic crater rim disappeared beneath layers of material, leaving behind the broad, gently sloping plain we see today. This low elevation is what makes Utopia Planitia so compelling. The northern lowlands of Mars sit several kilometers lower than the southern highlands. If Mars once had large, stable bodies of water, gravity would have drawn them here. Any ancient ocean would almost certainly have covered parts of this region. In 1976, NASA's Viking 2 lander touched down on these plains, becoming the first spacecraft to directly explore Utopia Planitia. It returned images of a rocky surface under a dusty sky and conducted experiments searching for signs of life. The results were intriguing and controversial, and they remain debated decades later. More than 40 years later, the Jurong rover arrived in the same basin, landing about 1,800 kilometers from the Viking site. From orbit, the terrain looked smooth. On the ground, it revealed itself as rough and rock-strewn. Jurong examined these rocks, analysed their chemistry, and sent radar signals deep beneath the surface. There, 10 to 35 meters below the dust and stone, it detected structures that tell a different story. Not of the Mars we see today, but of a Mars that once allowed water to linger. A planet where rivers may have flowed, where waves may have shaped sediment, where oceans might have existed for long enough to leave a lasting imprint. The stillness of Utopia Planitia hides a more dynamic past. The flat plain was built slowly, layer by layer, over immense spans of time. Some layers formed from wind-blown dust settling during quiet intervals. Others may have been laid down by water, sediments carried and sorted by ancient currents, recording direction and energy in their angles and arrangement. To read that history, scientists must look beneath the surface. Ground-penetrating radar reveals boundaries between layers, subtle slopes buried far below today's landscape. This is what Jurong uncovered: structures aligned in a consistent direction, with the angles that closely resemble coastal deposits on Earth, patterns that are difficult to explain without water. These layers do not shout their story. They remain hidden, patient, waiting to be noticed. They remind us that planetary change does not always announce itself with violence, but often unfolds quietly through processes that repeat over millions of years until the landscape itself becomes a record. This is how we reconstruct the past of a planet we may never walk upon as it once was, slowly, indirectly, by listening to what remains long after the waves have stopped and the planet has gone quiet. If you'd like to continue exploring these quiet stories of planets, deep time, and forgotten oceans, consider subscribing. There are many more worlds waiting to be listened to.